subthreshold current. So far we talk about the current mostly above the threshold. Then we have the saturation current or this linear or trial current. And we talk about that below the threshold, the current is almost zero, but it's not completely zero. So we will talk about why is that. So this is the reference chapter and Professor Asif Khan's video. Okay, so let's talk about this problem. So ideally, this is what you want, okay, for the switch, for perfect switch. So what do you want? You want below the threshold, the current is zero. Above the threshold, you have a large current. It's like the switch for your light bulb, right? You want to completely turn off the switch. This is what you want, okay? But in reality, it's not like this. So in reality, this is what we derived before, right? This is IDVG curve. Okay, this is IDVG, and here we have a threshold voltage about 0.5 volts. And above the threshold voltage is not abrupt, like this ideal case. The current will gradually increase, and we know that this is the saturation region and this is the linear region. So this is the IDVG curve, what we derived before. And we have this kind of plot in the previous section. So here what we are going to discuss is what happened here. This is below the threshold, and we call it a subthreshold, from 0 to 0.5 volts in this region. So far we say this is off, okay? And the current is almost zero. In reality, okay, if you draw the IDVG curve from the linear scale to the log scale, this is what you will see. So far you have seen this linear scale. Linear scale, that means this current is in the linear scale. It's just a linear, 200, 400, 600. But if you plot this linear scale into the log scale like this, you are going to see this region. Because this is so small, this current is so small, you have to use log scale to see this current. Below the threshold, around here. So this is log scale. You see this is 5 orders. So this is exponentially small current. It's not zero, but it's very small, exponentially small. And we call this as the subthreshold current. So previously we have a zero here, but now we will replace that zero with this subthreshold current, which is non-zero, but it's very small. As you approach zero gate voltage, this current will exponentially reduce. So here, of course, we need to have some drain current. So when this subthreshold current happens in this condition, when the gate voltage is smaller than the threshold, but still you have a non-zero positive gate drain voltage. The drain voltage needs to be larger than zero. Okay. So this is when you have the subthreshold current. If your drain voltage is zero, of course, then current is zero, because this is the current is coming from the, let's say, the source to the drain. The electron, as they travel from source to the drain, or current comes from the drain to the source. If the drain is zero, then of course current is zero. But here the drain is not zero, drain is larger than zero, but the gate is smaller than threshold, which means the channel is not completely formed. It's not strong inversion of your channel, because we talk about the threshold voltage That's defined as a strong inversion when the surface of your electron density surface is as large as the whole density in the bulk. But here, since the gate voltage is smaller than threshold, the channel is not completely formed. Okay, but still you can have some current. So let's look at this from this diagram again. So this is what we have seen before. This is above the threshold. We use those inversion electron density as a source and the drain and in the middle, and then we derive the IV equation above the threshold. And then this is the MOS band structure in the strong immersion at the surface. This is what you have seen before. And the high amount of mobile carrier above threshold voltage, which is controlled by the gate voltage minus threshold voltage and divided times the COS. So this is capacitance times the effective voltage that controls this amount of charge at the surface. But let's look at the weak inversion at the surface. This is below the threshold voltage, but still you have some gate voltage. Then you bend down a little bit. So here this is like a weak inversion before it reaches the threshold. So the surface is already kind of N-type. You have some electron, but not as many as the hole in the bulk. So in this case, you will see this surface has a little bit additional electrons. So this bulk, this kind of electric charge is due to the dopant. So only here, a little bit, this little peak here is the weak inversion electrons below the threshold. So this is the course of the current below the threshold. Or in other words, from the band diagram along the source drain direction perspective here, this is what we are going to have, right? So this is the source, and this is the channel under the gate, and this is the drain. And then we have this kind of band diagram. So if the gate voltage is not large enough, so still you have this is the barrier height towards the source side. So here what matters is the electrons that are over this barrier. So if you look at the Fermi function, so those electrons, as I said, exponentially decay electron with a larger energy. So those electrons can be over this barrier top. So actually to the drain side, you will also have a little bit electrons over the top of this barrier. But since the drain voltage is pushed down the band, so here you have even smaller probability. So actually the electrons, this is tend to diffuse over this barrier. This is due to diffusion. So then you have large diffusion here, small diffusion here. That contributes to the subthreshold current. So this is unlike the above threshold. For example, the last case, if this is above threshold, then this height is very small, and you have a lot of electrons over this barrier. And then after they are over this barrier, then they will be accelerated by the field. This is like a drift. But in the subthreshold, here the barrier height is so large, and this slope is not very large. So what matters is the electrons diffuse over the barrier. But as you can see here, the electrons of the source tend to diffuse the barrier to the right. And also you have some probability for the electrons in the drain diffuse over the barrier to the left. Then the net current is the difference between those two. So then here we consider the weak inversion charge density. Let's say weak. So here this current, this electron density over the barrier, this is of the interest. But we know this electron density exponentially depends on the barrier height here. And this barrier height is modulated by the surface potential, phi s. So that means here the electron density towards the source side here is given by this formula. Some n0, let's say some initial electron density, and then exponentially depends on the phi s, the surface potential. That is the bending at the surface. Because that bending is going to reduce this barrier height. This bending is this bending. This is phi s, right? Phi s is going to bend down the band at the source side. Then it will bend down the source barrier height. So then this phi s determines the source electron density that can be over the barrier. Then that means the current is proportional to this number of electrons that can be over the barrier. So the current to the right, we use I plus represent this current, I plus. Then the I plus, let's say some I0, which is some coefficient, and then exponential dependence on the phi s over kt. Similarly, to the drain side here, the electrons that are over the barrier will be determined by the surface potential plus the drain voltage. Because here the drain voltage will bend down here, make this less probability. So then this phi s needs to be minus Vd here. So that is the effective bending of the barrier at the drain side. So you have the I left. Here we use I minus represent the current to the left. So you have the current to the right, current to the left. Both of them are diffusion currents. Then the total drain current is the net current of those two. So will be this I0 exponential phi s kt minus and you can take the common term out. You can take the common term q phi s kt out. Then what you have is here. So this is the net current. So we consider the diffuse of the electron from the left to the right, from the right to the left. Of course, the diffuse from the left to the right is higher than the right to the left. So you have this equation. This, I just this is exactly this one. So I just show it again here. So this is when the gate voltage is below the threshold, so-called cutoff region or the subthreshold region. And then we eventually need to derive the drain current as a function of the drain voltage as well as the gate voltage. So here we need to know what is the gate voltage. Okay. So the phi s, if you recall, phi s is the bending of the band, but the gate voltage is what you applied here. And you have seen this before. The gate voltage actually drop on the oxide and then the phi s. So the phi s is just a portion of the gate voltage you apply. So we give a factor of this portion as the body factor. So the change of the gate voltage respect to the change of the phi s respect to the change of the gate voltage is defined as 1 over m, and then we call this is as a body factor. So here basically we replace the phi s with Vg divided by m, because if you apply 1 volt on your gate, maybe only 0.5 volts will change the phi s, because another 0.5 is dropped on the VOX, the oxide voltage. So here then if we replace the phi s with this Vg divided by m, so you will get this one. So this is the subthreshold current equation. And typically here, because the drain voltage is larger than, let's say, if the drain voltage is larger than kT, kT is the thermal voltage, like 26 millivolts. If your drain voltage is larger than the 26 millivolts, which is typically true, then you can look at this term, because it's exponential to some negative number. And this negative number, if this negative number is large, you know, exponential function, this exponential function will approach 0 to the negative side. So that means this will approach 0. So you can ignore this term. Oops. Why is it like this? So you can ignore this term. Then the drain current will be exponentially depends on the gate voltage. That's why when you draw this curve, if you take the log, ID, you will get log N0 plus QV QG MKT. So if you take the log scale of this equation, both sides, so you will get this one. So that means this is actually the log 0. And then this is a linear function with gate voltage in this log scale. And the slope here will be this 1 over MKT. So that's why here we explain the current exponentially depends on the gate voltage if it's smaller than the threshold. So any questions here? Okay, so if you modify